In this video, we will be looking at double displacement reactions and do some examples that illustrate double displacement reactions. First, we want to talk about what a double displacement reaction is in very general terms. So sometimes we call these double displacement reactions precipitation reactions, as a solid will sometimes form as well. Another name these double displacement reactions sometimes go by are metathesis reactions. So in a double displacement reaction, you're looking at a reaction between two ionic compounds. That's your key that you're dealing with a double displacement reaction. What will happen in these double displacement reactions is the ionic compounds will switch partnerships in the reaction. This follows a very predictable pattern. So we're going to look at this pattern. So I did this in a very general way, and then we'll look at some specific examples later. So I have ionic compound AB, with A being the positive ion, B being the negative ion. Now I'm going to react that with compound CD, also an ionic compound, with C being the positive ion, D being the negative ion. So what I'm going to do is I'm going to mix and match partnerships. I'm going to take the positive A, which is currently paired with the negative B, and I need to pair this with the other negative ion. So my new partnership is going to be AD. The other two that are left over, I still have negative B left over and positive C. I need to pair those as well, so my other compound will be CB. The C has to come first because that's the positive ion. We always write ionic compounds with the positive ion first. For these double displacement reactions, we no longer need to be told what the product is. We can figure it out from the reactants that we have. Previously, anytime you had a reaction, you had to be given the entire reaction, reactants and products. Here, we're now at the stage for these type of double displacement reactions where you're not going to be given what the products are, you're going to have to figure those out. So now that we've seen the general pattern, let's look at some specific examples. So aqueous solutions of lead nitrate and potassium chloride are mixed. We want to write out the complete molecular, ionic, and net ionic equations for these. So what we're really doing is we are going to mix and match these ions. So we want to figure out what's going to be produced. What are we going to make out of this? So the first step is to predict the products. We need to take our ions and mix and match those. So the first step is looking at what ions you have. So the lead nitrate, I have a lead ion at +2. And I also have nitrate ions. The nitrate ions are going to be -1. It doesn't matter that I have 2 of those at this point. We just need to list what type of ions we have present. We can deal with the exact numbers later when we go and balance the equation. So for the lead nitrate, I have lead +2 ions, and I have nitrate ions. For the KCl, what do I have? I have potassium +1 and chloride -1 ions. Now I need to mix and match these ions. I need to pair the lead, who's currently with the nitrate, with a new ionic partnership that's going to be the negative chloride ion. So I need to pair the lead and the chloride. Well, how do I pair those? Well, I can't just randomly throw them together. I still need to achieve charge balance. The lead's +2, the chloride's -1. So what I'm really going to need is I'm going to need 2 chloride ions for that in order to have charge balance. So my new formula is going to be PbCl2. Now for my other partnership, I'm pairing negative nitrate ions with the positive potassium ions. Nitrate's -1, potassium's +1. So to have charge balance, I just need 1 of each. So my other compound is going to be KNO3. So in kind of the stage that we're at here, we were able to successfully predict the products. Next up, we have to decide whether those products are soluble or not soluble. And to do that, we need to use the solubility rules to decide if these are going to be soluble or not. So you have to memorize these solubility rules. So our solubility rules for chlorides say chloride's generally soluble except when paired with lead. And here we're paired with lead. So being we are paired with lead, that's going to be a solid here. That's not going to be soluble. For our other compound, things in group 1A, potassium's in group 1A, those ions are always soluble. Also, nitrate is always soluble. So the other product's definitely going to be soluble. So our precipitate is going to be the PbCl2. Our last step is to balance the equation. Just like all of our other equations had to be balanced, these double displacement reaction equations have to be balanced as well. So here you can go ahead and use the tally chart. Sometimes you don't need to. Sometimes you can just kind of quickly look and see what you need. But you need to successfully balance this. So getting those two coefficients in there to get everything balanced. What we just wrote is sometimes called the molecular equation. That's our standard form. There's a couple other different forms of this that we can write that we're going to see, but we generally start with this molecular equation. Let's kind of quickly go through the steps again. First, predict the products. Mix and match the ions. You are not worried about balancing in terms of balancing an equation at this state. You first have to just get the correct formula of the products. Once you have that, you're going to use solubility rules to decide if those products are soluble. Then lastly, you're going to balance that equation. So molecular equations are considered the standard form of the equation, but what the molecular equation doesn't do a good job of is it doesn't do a good job of showing those ions that are actually in solution. So what we sometimes do is sometimes we write an ionic equation from that molecular equation, because the ionic equation does a little bit better job of showing exactly what you have in that solution. So I just rewrote our molecular equation that we ended with, and then here are the steps we're going to do to go from this molecular equation to the ionic equation. We're going to take soluble ionic compounds. Remember, soluble ionic compounds will be strong electrolytes. They're going to have charges. They're going to dissolve. We're going to show how they really look in the solution as ions. If we have a precipitate, we're going to leave the precipitate as written. We're not going to make any changes to that. So we're going to take our molecular equation and write the ionic equation from that. So here's how we do that. Lead nitrate is soluble. Our PbNO3,2 is soluble. So what kind of ions do we have? Well, these aren't really together. That's what the AQ means. These aren't really together. These are split up into ions. So we're showing that in this ionic equation. What do I have? I have one lead ion with a +2 charge. What do I also have is I have two nitrate ions. They're not linked together. They're actually separate. So I need to show them as having two in quantity, but not actually being bound together. So that's how we're going to write our nitrate ions out like that. They're not together. In the top, we're showing them kind of together. What's really happening, though, is they are not together in that way. Same thing with the potassium chloride. 2KCl that is soluble. That's a strong electrolyte as well. That's going to split up into its ions, so I'm really going to have two potassium ions and two chloride ions. Now for the product side, the lead chloride that we have here, the PbCl2, that's a solid. That's our precipitate. That's not dissolved in solution. That hasn't been dissolved by the water. That hasn't split up into individual ions. The lead and the chloride are still together. We leave that together when we write our ionic equation. For the 2KNO3, what do we have? Well, this is soluble, so we need to show those ions. Two potassium ions soluble, two nitrate ions that are soluble. One key thing you want to make sure you do, and sometimes people get sloppy and don't do this, you need to show charges for all of your ions. You can't get sloppy. This is an ionic equation after all. If you're not showing those charges, you didn't write an ionic equation. So you have to make sure you're doing that. It's kind of easy to get careless and sloppy and not quite do that. You have to make sure you're still doing that. You also have to make sure you're writing the states of matter in, whether it's a solid, whether it's AQ. It can kind of be easy to kind of forget to do that for a couple of them. You have to do that for everything. So what we just wrote is the ionic equation, and the ionic equation does a little bit better job showing all the individual ions that we have present. There's one last equation we can write from this, and it's called the net ionic equation. So, although the ionic equation clearly shows all the ions in place, it can be a little bit long and cumbersome. Sometimes we can write a more condensed way of showing that. So sometimes the net ionic equation is written. What the net ionic equation does is the net ionic equation simplifies the equation to just showing the things that end up changing in this. It shows the action for what happened in the reaction. So we want to look at how do we take our ionic equation and write a net ionic equation from that. So what we're going to do is we're going to look for things that appear on each side of the equation and cancel them off. These things that we're going to cancel off we call spectator ions. Chemistry is sometimes called the science of change. We often care about how things are changing. What changed in the reaction? And that's what this net ionic equation is going to do. It's going to get rid of any piece that wasn't directly involved in the change. So let's kind of look at our ionic equation. Now what we're doing is we're looking for things that appear on both sides of the equation. Very similar to what you may do in math. If you have the same thing on the left that you do on the right, you cancel those things off. So what do we have here? I see 2 nitrate ions on the left, 2 nitrate ions on the right. We could cancel those off. I see 2 potassium ions on the reactant side on the left, 2 potassium ions on the product side on the right. We could cancel those off. Now, when you cancel in math, it's a little bit different than what we're showing when we're canceling here. When you cancel off something in math, you completely got rid of it. It doesn't exist anymore. That's not what's happening here when we're canceling. Here when we're canceling, we're not getting rid of it. There are still nitrate ions present. There are still potassium ions present. By us canceling them off, though, what that is showing is that they didn't take part in the change. They weren't part of the change in this. They weren't part of the action. They were watching. They were spectating. They were seeing what was happening, but they weren't a part of it. That's why we call these spectator ions. They're there, but they're not actually involved in the reaction. Our last step is we just kind of bring down, just like in math, bring down what we didn't cancel. So lead ions, chloride ions, chloride ions. Our precipitate, lead chloride, our precipitate. And what we have is the net ionic equation. And the net ionic equation just shows those things that actually change in the equation. Just like the ionic equation, it's important to remember to write charges in where it's appropriate, as well as to write in whether things are aqueous or solids. So this was one example. Let's look at another example that kind of goes through this. In this one, we're going to be looking at aqueous solutions of FeCl3 and NaOH are mixed. We're going to write out the complete molecular, ionic, and net ionic equations from these. So what are we looking to do? We're going to react FeCl3 and NaOH, and we're going to try to figure out what in the world those are going to produce. So again, just like before, the first step is to predict the products. We need to mix and match the positive and negative ions. So I wrote out again the ions that we have in place. The FeCl3, well, that means I have Fe plus 3 ions. I'm also going to have Cl minus ions. If I look at the NaOH, what am I going to have? I'm going to have sodium plus 1 ions and hydroxide ions. So now I need to mix and match. Right now, the iron is paired with the chloride. So to mix and match the ions, I need to pair the iron with the hydroxide. So the iron is plus 3, the hydroxide is minus 1. So in order to pair those up, I'm going to need 3 hydroxides for every 1 iron in order to achieve charge balance. Need to do a similar process with the other ionic pair. Now I'm going to pair the chloride ions with the sodium ion. Chloride's minus 1, sodium's plus 1, so what's my formula going to be? NaCl. Remember, positive ion always comes first. So now I've successfully predicted the products. FeCl3 plus NaOH will produce FeOH3 and NaCl. Our next step is to use solubility rules to decide if the products are soluble. Again, you have to have these solubility rules memorized. So let's look at the FeOH3. The FeOH3, if you look on your solubility rules, you're going to find that the hydroxide ions are generally not soluble unless they're paired with something else that's very, very soluble. Here, this is going to be our precipitate. Iron is not going to allow the iron to be able, iron is not going to allow the hydroxide to be soluble here. This is going to form a precipitate. This would not be one of the exceptions. So here's going to be our precipitate. NaCl, well, we kind of recognize salt soluble in water, but kind of using the rules. Anytime you have sodium ions, they're almost always going to be soluble. Chloride is going to be soluble unless it's paired with certain specific things that would make it insoluble. So we're going to have NaCl be soluble, the FeOH3 not be soluble. Last step is we would balance the equation. Same techniques we've been using before. Remember, you don't necessarily have to split apart the polyatomic ions. You can balance them as whole units. You can use the tally chart. Sometimes you don't need to. But after you balance the equation, remember we've done this lots and lots of times already. I'm not showing the specifics of this. You need to just quickly then balance that equation. So then we would have our molecular equation. Next up would be to write out that ionic equation now. So for the ionic equation, remember, molecular equation did a good job of being kind of concise and being a standard form, but it doesn't show the ions that we know actually exist. So we're going to write that ionic equation from the molecular equation. We're going to do the same thing we did in the previous example. We're going to take our soluble ionic compounds, those strong electrolytes, and show how they really look in the solution as ions. Just like before, we're going to leave the precipitate as written. We're just going to bring that down as written. So to start this off, the FeCl3 is soluble. So what are we going to do? We're going to have iron plus 3 ions and 3 chloride ions. Remember, these chloride ions aren't together anymore. They're separated. Each chloride ion is now individually surrounded by water molecules. That's what this means when we say FeCl3AQ. We really mean we have separate iron ions and 3 separate chloride ions. We're going to do the same thing for the sodium hydroxide, 3 NaOH. That's soluble, so I need to split that up and show how that actually dissolved. 3 sodium ions, AQ, 3 hydroxide ions, AQ. For the FeOH3, this is our solid. This is our precipitate. This has not dissolved. This is not split up into individual ions. These ions are still all together. I need to show that. I'm just going to bring that down as is. The NaCl, though, is soluble. So the NaCl being soluble, I need to split this up into 3 sodium ions and 3 chloride ions. So here we have our ionic equation. We kind of quickly go back and double check. We have charges for things. You got to remember to do that. We have states of matter for everything. So now we have this ionic equation. Now we're ready to move on and write the net ionic equation. So for the net ionic equation, although the ionic equation shows all the ions in place, as we see, it's kind of long. So we can shorten that up with a net ionic equation. Remember, this is showing just the things that are changing in the reaction. So how do we do that? We're looking for those spectator ions. We're looking for those ions that appear on each side of the equation, and we're going to cancel them off. These are those spectator ions. These are things that are not going to be involved in the actual change. They're still present, but they're not involved in the actual change. So when we're looking for these spectator ions, I see 3 chloride ions on the reactant side and 3 chloride ions on the product side. I'm seeing 3 sodium ions on the reactant side and 3 sodium ions on the product side. We can cancel those off. After you've found those spectator ions and have canceled those off, it's really just a matter of bringing down things you didn't cancel off yet. The iron plus 3, soluble. The hydroxide ions, soluble. And then our precipitate. So now we have our net ionic equation, just showing those things that change. The actual change that happened here were iron ions reacting with hydroxide ions to produce that solid FeOH3. We have states of matter for everything. We showed charges where appropriate. So here we have our net ionic equation. So being able to write these molecular ionic and net ionic equations for these double displacement reactions takes some practice. This isn't something you're going to be able to do just by looking at it. You have to practice doing some of these to make sure you're comfortable doing these by yourself.